Okay, so example 5 is asking about the limit as x approaches -2, two-sided limit of this rational function, this rational expression x squared minus 3x minus 10 in the numerator with x plus 2 in the denominator. And I think what we should do is we should go ahead and try to factor this numerator, right? Because this is a quadratic polynomial in the numerator. And so I could write this as the limit as x approaches -2 of, and then in the numerator, this is going to factor as x plus 2 times x minus 5. Because 2 times -5 is -10, and 2 minus 5 is -3. So that checks out. In the denominator, we have this x plus 2 factor. And really the trick here is that when x equals -2, then this function is undefined, right? This rational function doesn't take on any value there because the denominator would be -2 plus 2, and that's 0. But if we use a little bit of algebra, we realize that, hey, in this rational function, we can make a cancellation of those two factors. And based on what we know about rational functions, everywhere else besides x equals -2, this is going to behave just like the much simpler linear polynomial x minus 5. So we can take the limit as x approaches -2 of x minus 5. And this is actually pretty easy. If I just plug in -2 for x, -2 minus 5 is -7. And so here, for this rational function, x equals -2 represents a point discontinuity, like we've looked at earlier. Let's look at example 6. And example 6 looks a lot like example 5, except that we're evaluating a different limit. In example 6, we're concerned more about the limit as x approaches 3. So I can factor it just the same way I did before. So we factored the numerator as x plus 2 and x minus 5, and the denominator is x minus 3. Oh, I see. It's not quite the same rational function in the denominator. Now we have x minus 3. And that's what makes this interesting, because as I approach 3, I can't actually set x equal to 3, because that would be undefined. And now I can't actually even cancel out anything in the numerator and denominator. So that tells me this is no longer just a point discontinuity, like in example 5, but this is actually going to be an essential discontinuity. Let's think for a moment about what the right side limit would be. So let's think about the limit as x approaches 3 from the right side only of what we've got here. So x plus 2 times x minus 5 divided by x minus 3. And maybe, as I'm thinking about x approaching 3 from the right side, maybe I think I'm just going to try to substitute something that's just barely above 3. I'm going to substitute x equals 3.01 into this expression here. And so 3.01 plus 2 would be like 5.01 in the numerator. And then for this factor, x minus 5, well, 3.01 minus 5, that would be like, it would be like 1.99, I think. Is that right? No, that should be negative 1.99. Okay. And then in the denominator, 3.01 minus 3 would be 0.01. And so what I have is negative, because the numerator has a negative factor and the other factors here are all positive. And I'm dividing by a very, very small number. And when I divide by a very, very small number, it's going to make my whole fraction actually very, very large. So dividing by 1/100th is like multiplying by 100. And so here I've got about something like 2 times 5 is 10. 10 times 100 is about 1,000. So I've got something that's about negative 1,000. And you can check me on that if you want to. But if I put in something that's just barely above 3, I get negative 1,000. Interesting. Let me go in a different direction now and try the left-sided limit. So the limit as x approaches 3 from the left side. And we consider the same exact expression and see what we get. So, coming from the left side, let's sub x equals 2.99 into that expression. And so 2.99 plus 2 is about 5. It's actually 4.99. And 2.99 minus 5 should be like negative 2.01. And then the denominator, 2.99 minus 3, should be negative 0.01. So I have two negatives here in this fraction, which makes it a positive overall. And the numerator is about 10. And then I divide by 100th. And so this is going to be, roughly equal to positive 1,000. So think about that. On the left side of x equals 3, we're getting really, really large numbers, like positive 1,000. And on the right side of x equals negative 3, I'm getting really large negative numbers, like negative 1,000. And so you can see this is going to be an essential discontinuity, where on the left side, again, we're getting really large numbers, and on the right side, we're getting really small numbers. So it'll look like this vertical asymptote. On the right side, we approach, negative infinity, and on the right side, on the left side, we approach positive infinity around the point x equals 3. So the two-sided limit does not exist, by the way. The right-sided limit would be approaching, like I said, negative infinity, and the left-sided limit would be approaching positive infinity. Okay. And we came to this conclusion just by thinking, what would it be like if I picked a number that was just to the left of my limit point? And what would it be like if I picked a number just to the right of my limit point, right? Okay. Example 7, I've got another rational function, and I'm going to use exactly the same logic that I did before, where, again, I have the same numerator, I think. So this is still x minus 2 times x minus 5, x plus 2 times x minus 5. And then the denominator, this time, I have actually x minus 3 squared. And what's going to happen with that square now, as I'm taking the limit, right, of this? If I take the right-sided limit, which means I sub something just to the right of x equals 3, like 3.01, this is going to be something pretty much like what we had before. I can even cheat just for a moment and look up and see that in my numerator, I had 5.01, and I had negative 1.99, and then the denominator had 0.01, but now I have 0.01 squared, and 0.01 times 0.01 should be not 1,000th, but actually 1/10,000th, like this. And so on the right side, just to the right of x equals 3, I get a really, really large negative number. It's going to be negative 100,000. And you can check my math. And on the left side, if I sub in a number for x, an input for my function that's just barely to the left of x equals 3, like 2.99. Again, the numerator is going to be like the same as that I had before, which is going to be something like 4.99 and negative 2.01. And then the denominator will be 2.99 minus 3, so negative 0.01, but that's going to be squared, and when I square a negative, that makes this positive, right? And that means, again, my denominator is going to become 0.0001, And so again, it's going to be roughly equal to negative 100,000. So whether I go just a tiny little bit to the right of x equals 3, or a tiny little bit to the left of x equals 3, I get a huge negative number. And based on what I know about essential discontinuities in rational functions, I can assume, well, assume's not the right word for it, but I can sort of rationalize the idea that this two-sided limit on both the right and the left side, this is going to be equal to negative infinity. So whether I come in from the left side or I come in from the right side, I'm going to have a vertical asymptote here at the point x equals 3, where my function on both sides is approaching negative infinity as I get closer and closer to 3. Okay, so that's example 7. Example 8. Let's see what we get. I think example 8 looks like one of those where if I just try to plug in x equals 0, this will be undefined because I just have x in the denominator. I can't divide by 0. But maybe I can use some algebra tricks just to rearrange this a little bit. Like in the numerator, I'm subtracting two fractions, but they have different denominators. And there's a trick that we can use to make it so that we can actually perform that subtraction, find the difference, and I'll show you what it is. Let me just rewrite limit as x approaches 0. In the denominator, I have 1 over x plus 4, and I'm actually going to multiply this by 1. But what I mean by 1 is that, well, 1 equals 4 over 4, for example, and 1 also equals x plus 4 over x plus 4. And notice when you multiply anything times 1, it doesn't change the result, right? So like 7 times 1 is 7. And so whenever I multiply by 1 here, I'm not actually changing the value of the fraction. So this time I'm going to multiply by 4 over 4. And then I have subtract 1/4, and this time I'll also multiply by 1, which doesn't change the value of the 1/4. It's just something that I'm going to do to make this problem easier. Now, this becomes the limit as x approaches 0 of, over here, 4. And notice the reason I did this here is because when I multiply these denominators, x plus 4 times 4, and over here, x plus 4 times 4, these have the same denominator. So now I can actually subtract these things. I can do like 4 minus x plus 4 divided by x plus 4 times 4. And that's all in the numerator because my denominator is still x. So let's distribute this minus sign over here. So instead of having these parentheses, I'm going to get rid of that and write 4 minus x minus 4. Now, you might say, well, I have 4 and 4 minus 4, so 4 minus 4 is 0. That really leaves my denominator as just being negative x. Now, negative x divided by x in the denominator, I guess what I'm saying is whenever you divide by something, it's actually the same thing as multiplying by the reciprocal. Hopefully you've heard that before. So like, for example, if I have negative x divided by x plus 4 times 4 divided by x, all of that stuff divided by x, that's the same thing as multiplying by the reciprocal of x, so multiplying by 1 over x. And when I multiply by the reciprocal like this, you can see that x is going to cancel with that one. And what I'm left with is negative 1 over, and let me distribute this 4, so it's 4x plus 16. Okay. Now one thing I've gotten lazy about is writing the limit here, so let me correct that. This should be the limit as x approaches 0 of these things, and so what I'm trying to do here to solve my problem is take the limit of x as x equals 0. And so this 4x will become a 0, and this limit I can evaluate as negative 1 over 16. So this again appears like one of those point discontinuities that we had before, where if you just look at the function as it's given to you, you can't evaluate it at x equals 0 because of the x in the denominator. But if we do some, a little bit of rearranging with our algebra skills, we can actually get it into a form where we can directly evaluate it by plugging in 0 for x. Example 9. Pay close attention to example 9 because it's a little bit tricky, and I'm sure you'll have some of these on your homework. So we take the limit as x approaches 5 of root x minus root 5 over x minus 5. And notice if you plug in x equals 5 here, you'll get a 0 over 0 in your numerator and denominator. And if you don't believe me, feel free to try that out. But what I'm going to do is this. For the numerator, since I have root x minus root 5, and the denominator being x minus 5, I'm going to multiply by 1 again. And this time 1, for me, means root x plus root 5 divided by root x plus root 5. And when I do this, my numerator is going to become x minus 5, and in my denominator, I have x minus 5 times root x plus root 5. So seeing that my numerator and denominator have the same factor, namely x minus 5 in the numerator and x minus 5 in the denominator, I can cancel these. And I'm talking about the limit now as x approaches 5 of 1 over root x plus root 5. And if I plug in 5 for x, you can check this yourself, that this answer is going to be 1 over 2 times square root 5 in the denominator. So this is our answer. Again, maybe this is one of those point discontinuities because as it's given to you, this function can't be evaluated at x equals 5. But if we use some algebra tricks, we can rearrange it in a form where we can directly evaluate for the limit by just plugging in x equals 5. Example 10 says, approximate the value of this expression, the limit as x approaches 0, of 1 plus x to the power 1 divided by x to 5 decimal places. And for this, we're going to use Microsoft Excel. So in Excel, what I want to do is put together a little table. So on the left column, I'm going to put values of x, and on the right column, I'm going to put values of 1 plus x to the power 1 over x. What I'm looking for is the limit as x approaches 0 here. And let's do that. So maybe we'll do 1 as a place to start. And then for the next row, we're going to take that and just divide it by 10, right? So we get 0.1. And that's closer to 0, right? And if I just drag this down for several rows, what I'm doing on each iteration is I'm getting closer and closer and closer to 0. So I've got 1, 0.1, 0.01, 0.001, 0.0001. I'm getting closer to 0 by a factor of 10 each row as I go down the table. And in this column, this is where our Excel skills come handy. We type in equals, open parentheses, 1 plus, and then I reference cell A2 here for my x variable. Close parentheses, caret, which is shift 6, open parentheses, 1 divided by, and then again I'll reference cell A2 to get my x value. And it looks like if I evaluate at x equals 1, this expression becomes 2. And quickly with Excel, I can evaluate this for all sorts of x inputs. And the trick is, with example 10, is it wants me to evaluate that limit or approximate that limit to 5 decimal places. And so what we're going to look at is looking very closely at the B column. When's the first time that the first 5 decimal places are actually the same from one row to the next? And it seems like it's right in here. When I get to 2.71828, that 71828 is the same for row 8 in my table, row 9 in my table, and row 10 in my table, row 11 in my table, and it stays the same as I go down, right? So it looks like these are actually all accurate to 5 decimal places. I've gotten close enough with my x value that it works. And notice you can't plug in x equals 0 because that would be 1 plus 0 to the power 1 over 0. And you can't have 1 over 0 because we can't divide by 0, so that would be an undefined number. So it doesn't really exist here. I mean, it doesn't. This little function doesn't really exist at x equals 0, but we can approximate it, or we can actually find the limit anyways. This was this was a right-sided limit because we came in from something larger than 0. What if we came in from something less than 0, like -1? Let's see how that affects it. Not by much. So if I start from the left side, like at -1, and then I get closer and closer to 0, I still actually get the same stuff, right? 2.71828. That seems to be the trick. And maybe if you're looking really closely, you say, hey, this really falls apart at a certain point, right? This is supposed to be 0.71828, but at a certain point it falls apart. So is this really the correct limit down here? And the answer is no. The limitation is that when computers perform math, it's not exact, but they actually have to round off to a certain number of decimal places after each operation. And that's usually a really large number of decimal places. Like you can think about it like 15 decimal places. But if we're dealing with really, really tiny numbers, then the math becomes a little bit imprecise. Right, and so these are actually the correct answer in here, and this calculation becomes unreliable after about row 13 in this table. So those are all bad values. Okay, enough talk about example 10. Example 11 is telling me take the limit as x approaches 3 from the right side. So remember that plus sign after the 3 means this is a right-sided limit. And so why would this be a right-sided limit and not a two-sided limit? Well, if x is greater than 3, then x squared will be greater than 9. And so something greater than 9 minus 9 will be positive. And if we take the square root of a positive number, this is going to be a real number output. What happens if you take the square root of a negative number? The square root of a negative number is an imaginary number. So we don't want to take the square root of we don't want to take the square root of a negative number if we want a real number output. And so we say specifically that this is a right-sided limit because if we came from the left side, all of the values we would be calculating would be imaginary as we were approaching 3. Okay. Now, how do we evaluate this then? Well, you can actually evaluate this directly, right? Because if we plug in x equals 3 here, the limit becomes the limit as we approach 3 from the right side of square root 3 squared minus 9. And the limit of 3 squared minus 9 would be the limit of 9 minus 9. And 9 minus 9 is 0. Square root 0 is 0. We're talking about the limit as x approaches, well, we're talking about 0, basically. This is the answer. Let me show you what this looks like here. What does this function look like? Square root of x squared minus 9. If I use Desmos to graph it, you can see that the function exists and is defined for values greater than x equals 3 for these input values. And so we can talk about the right-sided limit as we approach from the right side. But notice the function is not defined in this interval between -3 and +3. So it wouldn't make sense to talk about a left-sided limit here, because the function doesn't have any values that you could notice as you're approaching 3 from the left side. Okay, example 12. We're talking about the limit as x is approaching positive infinity of 2 to the power 1 over x. And so one thing you can do if you want to think about these and sort of think to evaluate is what's happening as x gets larger and larger and larger. So maybe we can think about what would it be like if x were, let's think about what it would be like if x were 2. So if we talk about 2 to the 1/2 power, that's the same thing as square root 2. And square root 2, I don't remember exactly, but I think it's 1.4-ish. That sounds about right, but it could be wrong. It's somewhere in this neighborhood, though. And if you do cube root of 2, or 2 to the 1/3 power, if x is equal to 3, remember x is getting larger and larger as we approach infinity, we're talking about the cube root of 2, which I don't really know what it is, but it's definitely less than 1.4. And as we take larger and larger roots of 2, what we're saying is that, something times something times something for the cube root is equal to 2. But if I ask you what's 2 to the power 1 over 1,000, well, that's the 1,000th root of 2. What I'm asking you is, what is it that if I multiply it times itself 1,000 times gives me 2? And the answer is something just barely larger than 1, because if you multiplied anything times itself 1,000 times and it were less than 1, it's going to approach 0. If you multiply 1 times itself 1,000 times, then you would just get 1. And so we're talking about something that's just barely more than 1. And as that number goes up and up and up, the number is going to get closer to 1. So, maybe you can see this kind of logic. But what is the limit as x approaches positive infinity of 2 to the power 1 over x? Well, as the x becomes very, very, very large, 1 over x is going to be basically approaching 0. Yeah, you can think about it this way as well. 1 over x approaches 0 as x approaches positive infinity. And if you have 2 to the power 0, that would just be 1. That's probably a smarter way to think about it. I kind of got off in the weeds here in my own thoughts. But this is just sort of stream of consciousness. How would I solve this problem if I saw it for the first time? Because I am seeing these problems for the first time. But let's think about it this way. Let's do this. So just looking at the exponent alone, let's think about the limit as x approaches positive infinity of 1 over x. Well, think if x was a really, really large number, right? So let's think x is like 1,000,000, So here I let x become 1,000,000. We're talking about 1 over 1,000,000. This is a tiny, tiny fraction. And as x becomes larger and approaches positive infinity, that fraction will only become more tiny, right? So as, positive infinity isn't a real number, but you can imagine 1 over some number approaching positive infinity, 1 over some huge number. This is actually a tiny fraction. And basically, as we get tinier and tinier, what I'm saying is that we are actually approaching 0 with that fraction. So this limit, as we take, x going to infinity, and we take 2 to the power 1 over x, we're basically saying we're approaching 2 to the power 0, and anything to the power 0 is 1. Maybe that's a better explanation. And I think this is our last example with example 13. Let me change colors and do number 13 here. So we're talking about as x approaches negative infinity, we're going to consider what happens to 3 to the x power. And we'll start with a little sequence. 3 to the 0 power, 3 to the negative 1 power, 3 to the negative 2 power, 3 to the negative 3 power, and so on. Well, anything to the 0 power is 1. We just mentioned that a second ago. And when we have negative exponents, what it means to have a negative exponent is that you just put it in the denominator. So like 3 to the negative 2 power, well, 3 squared would be 9, but the negative 2 power makes it 1 over 9. And 3 to the negative 3, well, 3 cubed would ordinarily be 27, and the fact that it's negative 3 makes it 1 over 27. And 3 to the negative 4 would then be 1 over 81. And notice that these fractions are actually approaching 0. Because the numerator is 1 each time, and the denominator is going up by a factor of 3 each time. And we're not just talking about it, this limit being actually 3 to the negative 5th power, but we're talking about this being 3 to the negative huge number power, right? Because we're allowing x to approach negative infinity. And so as these fractions are approaching 0, we say that the limit here is 0. Okay.